Hi, everyone. My name is Tim Rupert. It was great being in Anaheim and getting to chat and work with people in person. But I'm recording this so that other folks who couldn't make it to the meeting can hear my talk. The title of my talk is In Situ Nanoscale Mechanical Testing to Isolate the Effect of Grain Boundary Complexions. Before I dive right in, I want to acknowledge the great early career people that I'm working with. Tianjiao Lei is a postdoc in my group, extremely talented scientist, and someone who's looking for faculty jobs right now. So I would encourage anyone who has postings to look out for Tianjia. She's really a force of nature. Jenna Wardini was a graduate student in my group who did some of the experiments I'm going to show as well. In the second half of my talk, I'm going to talk a little bit about some nanostructured aluminum alloys, and that's been part of a collaboration with Dan Gianola, who's a professor at UC Santa Barbara. Just to provide a little bit of motivation for the work I'm going to show you here, in my lab, we're very interested in trying to avoid premature failure in nanocrystalline metals. The basic idea is that we have known for a long time that as we go from microcrystalline to nanocrystalline materials, we can get rapid increases in our strength. So for example, this palladium sample can go from having a strength of under 50 megapascals to a strength of 200 megapascals. The problem is that the materials tend to become much more brittle during this process. And here you can again see this in this nanocrystalline sample failing after very little plastic strain. You can see extra evidence of this in fracture surfaces of nanocrystalline materials. In terms of mechanisms, it turns out that the grain boundaries are very important in these instances. And the critical event seems to be absorption of dislocations into the grain boundaries. I like these nice illustrative examples from Eric Bitzek, where he isolated dislocation absorption into an interface with molecular dynamics. If you look at this simulation, after the dislocation is absorbed, you could say, okay, there's no defect inside of the grain. Everything's back to normal. But it turns out that that process of absorbing the dislocation can change the grain boundary. On the left here is before, and the right after, looking at atomic stresses. This section of grain boundary I'm highlighting right here now has high tensile stresses. And those are the sites that are going to be primed for nucleating cracks. So with this mechanism in mind, we can say that grain boundary behavior is key, and we can start to ask, can we manipulate grain boundary structure to improve damage tolerance of nanocrystalline materials? The pathway we've been going down is an idea of trying to utilize structural disorder at the boundaries. Some of the motivation from this comes from observations in a model system that was sputter deposited by Morris Wong and colleagues. What they did is they deposited nanocrystalline layers and then interrupted the deposition to make a solid state amorphization copper zirconium layer. And the basic idea is you can think of this as a little artificial disordered interface. And these authors found that these materials were both stronger and more ductile than the pure nanocrystalline copper. We've studied this mechanism again in the context of dislocation absorption, and we find that having a disordered or amorphous interfacial film can delay crack nucleation. If you have an ordered boundary, you absorb dislocations very quickly, create a crack when you have to spread out that Berger's content. In contrast, an amorphous region can distribute the plasticity across the wider volume of material and delay that cracking. If you want to start to think about how to use that in a practical, real material, we can take advantage of the fact that there's been a lot of work in recent years on designing and manipulating interfacial structure. And I'm just showing some examples of the variety of interfaces you can get in metallic systems. You can have clean grain boundaries or normal grain boundaries. Of course, all the complexity of different tilts and disorientations is in there. And you can start to have ordered segregation patterns, but then also you can have discrete nanolayer films at the boundaries. And often these discrete nanolayer films can be amorphous. This is showing some analysis of the thermodynamics of a structure like this from Jean Luo's group, where they were talking about how you can stabilize an amorphous film with a uniform thickness at that boundary. In my group, we want to make these things in nanocrystalline systems. We use mechanical alloying to make whichever composition we're interested in. We heat these things up to high temperature. This allows for segregation of whatever dopant atoms we add to the grain boundary region. But it also allows for a pre-melting transition to occur. So just the interfacial region can melt. And then we can run a nice set of experiments and control grain boundary structure while keeping everything else constant by tuning how we cool down this material. So if we rapidly quench we end up going in and looking with high resolution TEM and often finding amorphous grain boundary films, just showing sort of two different views of these features. In contrast, if we take that exact same sample and we slowly cool down to room temperature, repeat that characterization, we find that we never see these amorphous films. We only get these ordered or boring grain boundaries in our sample. So what I want to sort of dig into today are two distinct goals. I want to first poke at this idea that this grain boundary state can affect the flow and failure of nanocrystalline materials. And to do that, I'm going to show you a case study in this copper zirconium system we've been working on. And again, isolating, just changing whether we have ordered or disordered boundaries in our system. And I also want to show you how this type of idea can be useful in more advanced nanostructured systems. I'm going to show you a system where we have reinforcements on multiple length scales. We have grain boundary segregation, amorphous complexions. We have different precipitates with different length scales. And we're going to use this case study of these aluminum, transition metal, rare earth alloys that we've been working with. The common theme is we're going to use small scale testing. It fits with the theme of this session, and try to poke at this failure of these materials. So let's start with the first one. Just to give a brief introduction to the experimental techniques we're going to use, we use the focused ion beam to make micropillars or microtension samples. One thing we are careful about is trying to avoid tapered pillars. So if you just do annular milling from the top, you'll end up with a tapered geometry where the top is a smaller dimension than the middle and bottom. And if you do this, for example, for a microcompression experiment, you get all the plasticity localized at the top. That might be useful if you're trying to look at how something fails, but it's not very good for extracting out quantitative information. So what we do is we use a lathe milling technique, first brought into play by Mike Uchek and co-authors, where you basically mill from an angle and rotate the sample around and keep doing that over and over. And what you can get are these nice taper-free pillars. We also try to follow other best practices from prior work. I'm showing an example of some mechanics analysis from KT Ramesh's group. They were looking at the effective taper angle, fillet radius, and also the aspect ratio of these pillars. For example, if you have a pillar that's much too long, you'll end up getting buckling during your compression experiment. The other thing we have to consider is what's the dimensions of the pillars with respect to our microstructure. Now, what we want to do, we're looking at a nanocrystalline material, is we want to really get something that's analogous to a bulk experiment. We want to sort of get something that isn't looking at external size effects, size of the pillar, things like that. Luckily, there's been some nice work from Julia Greer's group showing that if you have about 25 to 30 grains through the diameter of one of these pillars, you end up getting mechanical properties that are independent of the specimen size. So we're going to sort of keep that in mind as we make our samples. So anyways, we can go through and make these little pillars in our materials of interest. In this first study I'm going to show you, we were actually putting these directly into powder particles. And later on, we consolidate up, but then run the same type of mechanical testing experiment. And in our case, we were making sure that these pillars were big enough so that we were getting millions and millions of grains inside of them. The data I'm going to show you first is from a slight modification of that microcompression I just showed you. It's a microtension version. We actually go and get a particle that's along an edge that's been polished in the sample. We do the early stages of top-down milling to get the rough shape of the pillar. We use our lathe milling to get a nice taper-free pillar. But what we do is we leave this little top cap on here. And that's something that we can come in and grab onto and pull on to do a tension experiment. We do this with a femtotool system. Basically, on this end, we have a nice force sensor with a little silicon tongue that sticks out. But we can use the fib to pattern that so that it matches up as the inverse of this little top of the dog bone. You can see that on the bottom here. So this little tip can now be brought down, brought back, and used to pull and deform that sample. So what I'm going to show you here are two in situ SEM microtension movies. The sample on the top has the ordered grain boundaries. The sample on the bottom has the amorphous complexions. And as we pull on these, we see quite a big difference in how these samples fail. So the top one fails very abruptly, brittle fashion. And we see plenty of flow and plastic strain in this bottom one. If we zoom in afterwards, we can start to see the same behavior a little bit more clearly. Again, not much plasticity in this top case, plenty of plastic flow in the bottom case. the fracture surfaces even look quite different. And although I'm not going to spend much time on it, this is consistent with some older, sort of more crude experiments we had run. If you just do microcompression, the sample with the ordered grain boundaries starts to crush and crumple. In contrast, the sample with the amorphous complexions ends up having stable plastic flow. And you can even see this in these bending experiments. So if you make a pillar and try to bend it with a micromanipulator, it fractures very early on when there's ordered grain boundaries, and you can get lots of stable plasticity when you have amorphous complexions. We can start to look at the compilation of the different data we can pull out. I'm just showing all the stress strain curves we measured in this experiment. You can extract out things like what's the tensile strength, what's the strain to failure. One thing that comes out is we find that the samples with amorphous intergranular films are a little bit stronger than those with ordered grain boundaries. Okay. But if I look at this data and I start looking at the strain to failure, I find that these data points for those two sample sets more or less give the same value. And I'll sort of explain why in 1 second. Before I do, I just want to point out on this plot where we're compiling all this data from the experiment, there's a few outlier points, these open data points right here. It turns out that although we were aiming for sample geometries that were big enough, we ended up doing the characterization of our microstructure afterwards and finding our grains were a little bit larger than we had thought they were going to be when we first started. So those two open symbols are just samples where the diameter divided by the grain size is a little too small to be reliable. We include them, but we're not going to really use them to calculate anything because we think they're somewhat problematic. Anyways, if we look at the fracture surfaces, we can start to understand why strain to failure is not incredibly reliable. Whenever we always see that these samples fracture and fail at what I would call sort of an extrinsic defects. It's not something that's part of the actual internal microstructure. It's something like some carbide got formed during the ball milling process or the annealing process, or you have a hidden pore where as we were sort of mashing these powders together and making other larger powders, there was some little open space in there. The reason though I'm saying those are extrinsic and not really representative of our material is you can get rid of these things. You can change and clean up your ball milling process. You can hot press your samples, get rid of these pores and things like that. So we don't think that strain to failure is the best metric. Luckily, there's other metrics for plasticity. We can go and look, for example, at the area reduction in these fracture surfaces. And here's where we start to see the differences in the samples play out. So the sample with the amorphous complexions has roughly double the ductility when using this area reduction metric. And again, it's just representative of the fact that you get much more plastic flow and necking of these samples. You can also make a connection with the shear localization you see in bulk metallic glasses. So often when you do a deformation experiment, you end up seeing that metallic glasses fail along some inclined plane. That inclined plane, it doesn't have to be 45 degrees. And in fact, the pressure sensitivity of the glass ends up coming into determining what that angle is. But in any case, you get this inclined angle. We can go and look at what's that failure angle for all of these different samples. And what we do is we can rotate around and find what's the sort of highest angle we can fit to that. And again, what we find is that the amorphous complexion samples seem to be more damage tolerant, and that appears here as a lower fracture angle. Because we're doing this in situ, we can also look at local strains. And one way we do that is we can pattern on lines as little fiducial markers. And rather than just looking at the overall strain in the cross section, we can look at the strain in individual regions throughout this sample. This top row is all undeformed samples. And the second row is all samples at the same amount of applied strain. The two sets of samples on the left have ordered grain boundaries. The two sets of samples on the right have amorphous complexions. And what we can do is do some image correlation and track those fiducial markers and look at what's the local strain within those different regions. On this third row, we're plotting on top of the image using colors. So yellow is high strain, purple is low. And that same data is shown numerically on this bottom row. The key takeaways from this are that you get very localized plastic strain in the ordered grain boundary samples. So you get this one region which has a high value, the rest is much, much lower, whereas it's much more distributed in the amorphous complexion samples. And you can see that as there's a sort of variation, a smooth variation and more coloring that has some yellow tint to it in this image. Just to make sure we're not sort of totally out of line with other things that are happening in the literature, we can go and look at what has come out in recent years. And it seems that this idea that disorder can be a beneficial feature when talking about increasing the toughness is consistent with other findings. This example shown on the page right now, this was a deposited sample. It was aluminum rich, but they ended up finding that they could get some disordered regions at the boundaries. These probably aren't exactly the same as what we get in our sample. We're heat treating, alloying, trying to find a local equilibrium state. This is probably more frozen in from the fact that you have a limited kinetics when you sputter down a sample. But in any case, the microstructure is similar, and you end up getting similar types of findings where you end up getting more stable plastic strain during compression in the nanostructured aluminum with these amorphous interfaces than you do in either the pure metallic glass or the pure nanocrystalline material by itself. And in fact, the schematic that they use to explain this idea of the fact that the plasticity ends up getting shared within this glassy region is quite reminiscent of that earlier study we did on the mechanisms. There's lots of other examples. I just want to show a few interesting ones. On the bottom left here, it's the same kind of idea. In this case, your crystalline part is a medium entropy alloy, chrome, cobalt, nickel, and your amorphous grain boundary region is heavily iron, silicon, boron. But the microstructure and the distribution of structure is very similar. And again, the crystal glass composite is the toughest one. It turns out this idea of disorder being beneficial also goes and seems to apply to chemical disorder as well. In this beautiful work right here, these authors found that the crystal interiors had long-range chemical ordering, but this region at the grain boundary was chemically disordered. And that could allow these folks to end up getting, again, a better compromise, or actually no compromise, a better combination of high strength and increased ductility. Before we move on, it's important to sort of ask yourself the question, does this all make sense? So we're saying that we added a brittle phase and it has a toughening effect, and that seems sort of counterintuitive at first. What I'm trying to pitch to you here is that it's actually not that crazy as long as we're adding a small amount of that brittle phase in an intelligent manner. What we have is a nanocrystalline material with some fraction of amorphous complexions at the grain boundaries, which are the weak sites. This is actually quite similar to what has happened on the other end of the spectrum. Amorphous metals by themselves are very brittle, but if you add small fractions of nanocrystals, usually in dendrite form, you can end up increasing the toughness of the material. And the idea there is these crystals can end up blocking shear bands and keep you from having one catastrophic shear band. So instead of just having one shear band across the sample like I showed earlier, you end up getting lots of different shear bands moving in different directions. And these get stopped locally by those crystalline regions. The end effect is quite similar. You can get a ductile material where without those features, it's quite brittle. And there's actually been some really beautiful work. I want to point off Gammer and coworkers had this really nice study recently where they were doing nanoscale in situ tests in the TEM and able to show how shear bands will work their way around these crystals. So it really shows how those are obstacles. So in one case, in the nanocrystalline case, you're delaying premature crack nucleation. And in the amorphous case, you're avoiding a catastrophic shear band. And the key thing here is that the flow mechanism, or that initial plastic mechanism, is not necessarily the failure mechanism, and that's okay. Okay, so moving on, I want to show you a more advanced example of how this can be useful. I'm going to move on to these aluminum-rich alloys. And the basic idea of what brought us to these materials is just we wanted to sort of optimize and amplify this type of effect. I'm not talking about alloy design today, but if we look at which material systems can accommodate these amorphous complexions, we can come up with some design rules that work pretty well. We have to be adding dopants that segregate to the boundaries. But once they're there, we want them to have negative enthalpies of mixing, 3 or more elements, and also large atomic size differences from them all. This last one is actually quite difficult. So sometimes if you're just putting together different transition metals, it's hard to get things that all have large size mismatches from one another. And that's actually part of our motivation for looking at these aluminum transition metal rare earth alloys. I'm going to show you some examples. We have aluminum magnesium yttrium, aluminum iron yttrium, aluminum nickel yttrium. We also have worked with some other rare earths like cerium as this final material and ended up getting similar types of results. These cases were not just sticking with the powders. We were interested in making bulk nanostructured materials. So what I'm actually showing you here is grain size. So it all stays below 50 nanometers, and pellet density as a function of hot pressing temperature. Okay. The key thing is look at the end. So we have grain sizes of a little bit below 50 nanometers, and we can get fully dense bulk amorphous materials. Just to show what that looks like on this bottom right, this is a piece, it's centimeter or so in diameter. The only limitation is just how big the hot press in my lab is. So we can and have made bigger samples as well. And just showing here, we can confirm that these microstructures are nanocrystalline. We can also confirm that we get amorphous complexions in these samples. One thing I mentioned in that copper zirconium system is that we had to rapidly quench down to freeze in these features. And just as a way of seeing how much better these alloys are, we can see these amorphous complexions even if we don't quench down. So the way we do this is we ball mill the powders, put them into a hot press it down. You can't really quench from that sort of situation because your whole press is hot. So what we have to do is basically turn things off and allow things to gradually cool down. It takes about 4 hours to get to room temperature. Even if we take 4 hours to do that, if we go in and do high resolution TEM and look at grain boundary structure, we end up getting amorphous grain boundaries in the sample. And they're pretty thick. They're 2 or 3 nanometers in this case. And in fact, we can end up seeing something that's representative of what the high temperature structure and really the true potential of these alloys if we take these bulk samples, refire them up to that high temperature, and then rapidly quench down. Well, this is showing a pellet where we did that. We heated that up to near the melting point to have the pre-melting transition, put it on a cooling block so it would rapidly quench down, then repeat that electron microscopy experiment. And here we find amorphous intergranular films that are 8 or 9 nanometers thick. So very, very distinct. And I haven't talked about the mechanisms exactly, but this type of thicker film actually should be better for that toughening effect that we're seeing. These materials are quite interesting because we also end up getting some second phase precipitation, but in interesting ways. One thing we see is we see the growth of these nanorod precipitates inside of our microstructure. These things actually start to grow from these amorphous complexion regions, and they grow into the grain interiors. Early on, when they're small, they have amorphous structures on the inside, although they crystallize a little bit as they grow. And if we look at the chemistry, and also we've looked at high resolution TEM of these features, we end up can extract out that these are aluminum carbide particles, but they have really interesting chemical patterning where they have dopant-rich interfaces. So the metal and the rare earth metal end up patterning along the outside of these nanorods. We also get sort of traditional secondary precipitation of intermetallic phases. These particles are generally tens to hundreds of nanometers, so they're larger than our FCC grain size that makes up the majority of our material. We end up getting between 10 and 20% of the second phase, and they're just all intermetallic phases. So aluminum 3 yttrium, aluminum 10 iron 2 yttrium, and aluminum 19 nickel 5 yttrium 3. These are what you would predict from the bulk phase diagram. So there's no surprises there. On the right shows a sort of picture of what our microstructure looks like. We have what we call a hierarchical microstructure. So we have nanocrystalline grain sizes. We have segregation at all the boundaries. Some of the boundaries transition to become amorphous complexions. And then some of those boundaries serve as nucleation sites where those nanorod precipitates grow into the grains. And then finally, we have these bigger intermetallic particles within our microstructure. The end effect is we can get some of the strongest aluminum alloys that have ever been tested. We're showing here on the left side of this graph R3 data sets versus other samples that have been made in relatively bulk form. And we outperform both other nanocrystalline examples and also coarse grain samples, which are usually more complex in their chemistry and processing lab. What I'm going to finish up with is some small scale testing of 2 of these alloys. I'm going to look at the aluminum magnesium yttrium and the aluminum iron yttrium, because they provide some nice contrast with one another. One's the strongest, one's the weakest that we get, and they have nice differences in terms of the internal microstructure. We can see that by putting the characterization data together. So on the left side, you can see those nanorod precipitates in both. The aluminum magnesium yttrium alloy has a higher density of nanorods. Okay, so that's one difference. And in contrast, the aluminum iron yttrium has more of those intermetallic particles. So the big intermetallic particles that happen. It goes from 10% to 20% roughly. But every other aspect of the microstructure is roughly the same. So the grain size is about 50 nanometers for both. We get segregation at all the grain boundaries in both. We end up getting those nanorods where the metal and the yttrium segregate to the outside of the nanorod, and the interior is aluminum plus carbon. And then even the dimensions of the nanorods we get are quite similar. So on average, they're about 20 nanometers in length, about 4 or 5 nanometers in width. One interesting thing that comes out is we think that those nanorods actually end up nucleating those intermetallic particles, but that ends up giving us the big difference. So we go from 8.5% to almost 18%. So we have a doubling, about a 2x of the amount of intermetallic precipitate in our microstructure. You can also see that in these chemical maps here, where the intermetallics are more uniformly distributed in the aluminum iron yttrium than the aluminum magnesium yttrium. I'm going to go through and show you some small scale testing. We're going to do micropillars here, made the same way I mentioned earlier, so I won't spend too much time on that. On the left side, I have all the stress strain curves for these samples. And if you look at this, first you can sort of imagine that you see lots of variety in the outcomes here. But what I'm going to show you is that really everything here can be put into 2 buckets, some which undergo homogeneous flow and others which undergo shear banding. And I'll show representative examples of this. On the left, the sample is getting deformed, smushing down, don't see any localization. And on the right, we see an obvious shear band form during that deformation. Let's look a little more closely at these failed pillars. So in the case of homogeneous flow, we don't see any movement out of the compression direction. Because we're compressing these to 30, 40%, eventually small misalignments end up pushing the pillar over to the side a little bit, but there's no localization of plastic strain that happens. It's just sort of limitations on the ability to align perfectly. And we can contrast that with the shear banding behaviors. In these cases, we can see that there's the sample has really localized along a given plane. I chose these 2 examples because I think they're very important. Some of these experiments look like you get significant strain hardening after plastic flow. I'll just pick this one, this diamond sample here. It turns out that that's not really plastic strain, but that's just an effect of the geometry. The shear localization happened such that the top of the pillar was the part that sheared down, very close to where the contact was happening. So you ended up increasing your contact area as this occurred. So rather than just the original contact area, it increased over time. And in fact, if you take this final stress and you correct it for the fact that the contact area is higher, it would bring this point down to here. So what that means is that we actually increase, we flow around 700 megapascals, and then we strain soften down to there if we had the correct normalization. So really what we're seeing is that these 3 bottom samples here are undergoing shear banding. This top set of 2 undergo homogeneous flow. And these are in fact the ones which have that have the highest strength that we mentioned, that we measure. And these are incredibly high. So 1 GPa for an aluminum alloy is sort of off the charts. The same thing happens for the aluminum iron yttrium. They just happen to be more clustered together. So the samples which go up and then come down, those are the ones which have homogeneous flow. The ones where we think we see that sort of artificial strain hardening, that's where we end up getting the localization. We can actually tie this effect to the distribution of those intermetallics inside of the microstructure. When we get homogeneous flow, we go and slice this and look in interior of the microstructure. We find that those precipitates are relatively uniformly distributed throughout the whole pillar. We have no regions which are dark and precipitate free. And we can contrast that with this pillar on the right. And I'll highlight this region here, which appears darker than the others. That's actually where we end up having no precipitates. And this pillar shear banded back into the page here, and that shear band location aligned with this region. We could go in and look at the effect this has on the microstructure. When we get this high local strain along a shear band, we actually get coarsening of the grains in that region. And some of those grains grow large enough that we can start to have stored dislocation networks inside. Just to confirm, we can use those TEM samples to look at and show that we don't get any of those intermetallics along that shear band path. So the bright regions in the head of stem show you the intermetallics, and the shear band avoids, or really it happens in a region where you don't have those particles. Just to show another view of this, I'm showing precession electron diffraction data, where again, you can see along the shear band, we have coarsening of the microstructure, which all appears as one single color. And I'll just say that this is consistent with some past work we've done where on nickel tungsten alloys, which these things are very stable against thermal grain growth, but if you end up having shear band, in this case, induced by very sharp indents, you can end up breaking up and having grain coarsening driven by mechanical stresses. So in these shear bands, we end up getting coarsening of the grains. So with that, I'll leave you with 3 take-home points. Hopefully I convinced you that amorphous complexions can improve the ductility of nanocrystalline alloys because they're damage-tolerant features. That within a hierarchical microstructure, homogeneity of the microstructure is very important. So these softer regions without intermetallic phases can end up being prime sites for strain localization. So if you want to avoid this, you need to have a better distribution of those hard phases. And finally, that even if a nanocrystalline microstructure is stabilized against thermal grain growth, strain localization can still drive significant coarsening. Thank you very much. I hope to get to interact in person with all of you soon, and have a great day.